So how are you going to manage your own security? Well, you're not. So one of the most common methods, and one of the problems that the U.S. government is having, and also the Canadian government, is who's launching the attacks against them? Their own citizens. Because their own citizens got hacked into, and now that hack is being used as a launch point to attack other people. This makes attribution a straight up nightmare. Because yes, you can totally see where the attack's coming from. It's coming from that home network router. And we put layers of protection around this. So for example, ISPs will often not allow certain traffic to leave their networks because they just don't want to deal with this mess. And they'll do that sort of scanning if they're at all confident. But if we're scaling to the size of the planet or even to the size of the United States, not all are. And most of this article is actually going on about simple network management protocol and just general complaints to turn this off. And could everyone please just go around and just turn this off? And then you sit there and think to yourself, why is it on by default? Which is a concern. All right, I'm just kind of rambling at this point. I'm sorry, there's a lot of smoke in my office this morning, and I think it's damaging my brain. The point is, though, that it's really hard to do attribution because usually the attacker is also a victim. And this makes it really hard to do things. This also means that the governments are weirdly very motivated to help the average citizen not be a victim. Because if the average citizen stopped being a victim, then we'd stop getting attacks from our own citizens. Unintentional attacks. And so you get silly notes articles like this that don't actually help anything. But this is also why sometimes you see requirements go out for things like standards for routers and what should be defaults. And for the longest time, if you install a Mongo database, this is another way of saying you're about to leak all your data. Because for reasons I do not understand, Mongo apparently by default just makes everything public. And then no one fixed it, and we would end up with these data breaches all over.
Oh, it's like that Bluetooth thing we had recently.
Which Bluetooth thing?
The one where the debug interface is accessible over Bluetooth, and they have default passwords.
That's actually much better. An attack that requires Bluetooth means that the attacker must be physically co-located, which at least improves the situation. An attack that can be done remotely over the internet is very bad. Which is why things like Spectre are so bad, because it is actually, in the original research paper, they actually have an example of how to run this successfully against Chrome using nothing but JavaScript. You can actually launch a Spectre attack remotely via a Chrome fully updated browser. It is very hard to do. All right. Today I will be going fast because this is the lecture I dearly hope all of you already know, and I'm always horrified to discover you don't. So let's talk today about how the internet works. That thing most of you have been using forever and you think you know how it functions. And admittedly, if you've been doing web development, a lot of what I'm about to say is blatantly obvious. But I find if I don't run this, I regret it later. So we're going to go through this fast. I'm mostly putting this up to remind you that man-in-the-middle attacks are a thing, and they can happen at so many points. Fast. The web is basically just another layer sitting on top of all the rest of the networking stuff we learned about. The only thing we didn't cover is DNS, which is what I'm about to cover. But pretty much the internet is just sitting on top of that networking, and that has implications. So we are actually going to start with URL. We are going to start here because I would be horrifically embarrassed if people came out of the security class unable to read URL correctly. And I do research on this, so I know how many of you can. I have multiple research papers on this. This is the one I do hope most of the people here can handle. I have put this question in front of a lot of audiences, including like 600 high school students who all swear to me that the correct answer is Facebook's main website, because the mobile website is m.facebook. The only group I think I saw get this very well correct that wasn't already in a security class was a whole pile of Chinese people that had come over and were doing a delegation group. And I don't know why, but they all got it correct and stared at me like, why this is even a thing. Most people cannot read URLs. So we've established that it's not Facebook's mobile website. We're going to go through these letters because this is a trick answer. It's meant to go and be in front of a large audience. So who thinks this is Facebook's main website will open? So if I go and type this URL, now it's trouble again this year. The URL up at the top, and I put it down here in this box. What's going to show up in this screen? Is it going to be Facebook's main website? No. Facebook's mobile website?
No.
AT&T's website? Mobile's website? All right, this is a trap answer. Who owns mobile.com? AT&T. So, as I said, it's a trick answer. That is actually the correct answer to say mobile because it's going to attempt to go to mobile.com, but it is in fact owned by AT&T. It's important when having large questions to have a scheme in there. Like postal addresses, links are read right to left. The big thing is on the right, the small thing is on the left. So there is a massive difference between Sydney, North NSW, Australia, and Sydney, Canada. Even though the first word and the first two letters of the next component are the same. Please don't catch an airplane in the wrong place.
In China, it's the opposite way. That might be why.
Maybe. Did they reverse the order?
It's the country first, and then the province, and then the.
That I don't think would improve the situation. That would confuse people more, actually, I think. But the point is that, they're read in this order. This is important. This is a study I did back in, I think, 2018. This study came about because I tried to give my class at the time a fun worksheet in which we were going to go and take apart URLs, and they were supposed to do it after a quiz because it's going to be fun, easy, and I watched them all crash and burn at CNN.com. And this horrified me badly enough that I went through and started actually researching how well people can read these things. So what you're looking at here is a whole bunch of about 2,000 online workers on crowd working websites. So these are people who use the internet every single day but are not necessarily computer science majors. And if you show them a URL that looks like this, profile.facebook.com, mobile.paypal.com, so something where the big company name is sitting in the domain, oh look, most of them get it right, but oh goodness, I mean, how are you screwing this up? There is an entire tale here that concerns me. If I flip it, this happens. They all say that those top two go to Facebook and PayPal. If you look at the way the majority of the population reads URLs, they skim for the big company name, and that's where it goes according to them. This is one of the many reasons that it is really stupid advice to give people to look at the URL on a phishing message. Because if you're looking at a scam message, how hard is it to get a subdomain of your choice? Not hard. There is no police that wanders around and says, you cannot have a subdomain Facebook. And yeah, this is a problem. So, millennials are dead in the middle of this problem. Which generation are you? No, never mind. Smoke. I'm going to blame smoke on things. It was really hard to concentrate in my office this morning. This is a URL. A URL is known as a Uniform Resource Locator. It's a standardized format for describing the. Oh God, I copied this. This is bad. Okay, the word location, I actually have fundamental, deep opinions about. So this shouldn't actually say this. Let's just say it's a standardized format for describing how to get to the resource via the internet. This is not a location. I will fix this slide. A location is an actual address. This is a set of instructions for how to find the location. Similar, very different. This is,
What is an example of location?
IP address. IP address would be a much closer example to an actual location.
But that's still the instructions to how to get to the location.
It is not as extreme as this. Keep looking at this guide because look at what I have up here. If you're thinking to yourself, I know what a URL looks like. How many URLs have you ever seen with a password in them? Okay, I've seen a couple people who maybe have. Why would you ever put a password in the URL?
Whether or not this was good practice or not is something else, but it was internal, like a port 8080, like a Jenkins server. So when we would be making requests or even to a local self-hosted GitLab within the company behind a protected firewall, we already had to log on with our employee credentials, and there was one, I assume there was one like admin or one user level password that could make requests. So we had to have that.
If you think back to the ages when we first invented this thing, when we didn't consider security particularly important, maybe you would actually like to log in with one command in which you just put your username and password in, because this is a set of instructions on how to get there, not necessarily the end destination. So you can put in, for example, your username. You've totally done this before. I'm getting ahead of myself. Okay, so we have the host component. This is usually subdomain, domain, top level domain. That's what I was just complaining about a whole lot. Most people not understanding. For example, this might be profile.facebook.com. You have the username. Most people have actually used this. I mean, how many people here have ever typed in SSH your username at the place you're trying to log into? Probably a lot of you. You never thought of that as part of the URL specification, but it is. And this is a common tactic that attackers used to use for a long time before the web browsers basically made this an illegal thing to type into a web browser. We used to be the case someone typed facebook.com at evil.com. Where was that going to go? It's going to go to evil.com. But it says facebook.com at the front. And this was a tactic that was very old, but it was used for a while. Where's that the port? We talked about ports, that's from networking. So for example, you might do https vanier.com port 80 if you're requesting this. Oh no, sorry. I don't know. Smoke. http vanier.com port 80. These are in conjunction. S is not done over port 80. Then you have the URL path. So that might be something like google.com/search. And then you have the query string afterwards. And maybe poorly, but so you might have to search and the query string. These are components of the URL. This is my rant at the beginning why I'm upset about that location. URLs are not addressed. There are instructions on how to get somewhere. You can get a URL that links you into, say, a database, which hopefully has the password you should be using, the username you should be using, the query string into the database to find the record you're actually looking for. These are designed to be very flexible. That means, though, that the computer has to do a bunch of interpretation to figure out where it actually needs to go. This runs us straight into the domain name system. So none of your computers, if you ask them, and you say, what URL is this computer? And it says, what are you talking about? I only speak IP addresses. Because computers are not addressed with URLs, they're addressed with IP addresses. URLs are just these nice things that are nice for humans and honestly aren't even that nice. This brings us to the domain name system, which is how you map between them. These are not static mappings. So it's the case that it should be obvious to everyone in the room that if you type facebook.com and hit enter, it's not the case every single person in this room will be required to go to the same server. In fact, while physically co-located means the odds are actually good, but if you're located in the United States and someone else located here, odds are you'll be sent to a different server. They do that more for load balancing, but it is not required to always be visiting the same one. So DNS is a dynamic map between that URL name and the IP address we'll visit. And that mapping is not static, it's very dynamic, and it can actually do load balancing as well. I just have a screenshot here. You can totally run this on your own computer. Just type in dig and then the place, and it will dump the mapping out for you. So at the time I did this, these are the name servers for Google. And these are their known IP addresses. A name server is in charge of managing a portion of that address, and I'll get back to that. You can query this for most things. You can just type like host or something, and it will tell you who has this google.com, for example, at that point in time had this IP address. And your computer will do these dynamic matches for you. You can play with it. These are name servers. Name servers notify other companies what Facebook's current IP address is. So similar to BGP, this is kind of proliferated across the internet. There's a lot of caching going on. A name server will announce what a name is. A lot of other servers will cache it. Your local computer also will often cache it. This whole thing comes back to what's called the top level domains or the root name servers. So these are things like com, edu, org, basically all the top level domains. These are all listed in a globally public list. And if you want to go look up something that ends with com, you go visit one of these in theory. So what I'm about to show you is what happens in theory. In practice, there's a mountain of caching. But if everything got flattened and you had to start from scratch, this is how you would visit Wikipedia. So you're asking, where is wikipedia.com? So the first thing it has to do is pull the root name server. The root name server, it says, where is .org? Root name server comes back and says, well, .org is controlled by this IP address. So then the DNS will go out to that IP address and will say, okay, this is the org name server. Can you please tell me where Wikipedia thing is? Wikipedia goes, okay, you can find that at this IP address. DNS then comes back to that IP address and says, okay, hi Wikipedia name server, I'm looking for www. What IP address? And it comes back with this IP address. And then your computer tries to visit it. Alright? As I said, a lot of caching. Most of the time your computer has seen the .com top level domain go past several times already and has cached this and skips the first one. It may also skip some of the other ones. But this is how it's managed. One side effect of this is, remember I mentioned before, what's stopping you from having a Facebook subdomain? Well, there's actually not a global list of all full URLs. All URLs are managed in a hierarchical manner. Org decides what's going on with org. If Wikipedia wanted to do facebook.wikipedia.org, what would happen is the DNS would ask it, where do I find facebook.wikipedia? And it would answer. I've seen totally legit websites online that do things like manage user manuals that have Apple as a subdomain. Why? Because they have a chunk of Apple user manuals and they have put them in a subdomain called Apple. There is nothing that stops a company from having another company's name as a subdomain because they are the authority on it. I said this has a lot of caching. So when a resolver does a lookup, usually keeps a record local. So I tried pulling this up on my laptop, but apparently I've done way too many privacy-related things on my laptop, and it's just such a mess that I can't demonstrate this for you. But if you go and you pull up the local cache on your own machine, particularly on Windows, you can pull this up. You can see where it's recorded you've been. And then it will not do this lookup again for a certain time frame. Okay, that probably makes sense, but we worry a little bit about security around it. Up until now, when I've been talking about man-in-the-middle attacks, I've been talking about them as if there's one message, or there's one TCP connection or TLS connection. But that's not how the real internet works. The real internet, you're contacting people all over the place. So the first place I contact when I want to go somewhere is not the place I'm going. First place I contact is its DNS server. So what security exists around that? The answer is quite sad, actually. So as of 1989, we came up with DNS. We introduced this thing called DNS security extensions in 2004. I apparently got rid of the slides for this, but the short version is no one adopted it. It was adopted by a tiny percentage of people, and pretty much no one adopted it. So we introduced this other thing in 2011. Again, very poor adoption. It wasn't until 2016 we even saw DNS done over TLS. The adoption started picking up here a little bit, but when I was in the United Kingdom speaking with GCHQ, they were talking about how one of their big contributions this year was to create a DNS server that actually supported TLS. And you're sitting there going, you are the central security authority in this country. And we haven't been doing this? So actually, it wasn't until 2019, so just before the pandemic, that Chrome even started doing DNS over anything encrypted. And they only did that inside the United States at the time. I think they rolled it out further. I didn't do the research. It wasn't until 2020, the middle of the pandemic, that Firefox started doing DNS over HTTPS. So DNS has been very poorly protected, and one reason for that is that it was originally run over UDP packets, which was introduced in 1989, which means that we didn't really have as much bandwidth as we have now, and the setup for encryption is actually quite heavy. But the request you're doing with DNS is just so light. I mean, imagine the TLS connection, right? First you have to do, first you have to start a TCP, a whole handshake, and then you have to do a TLS whole handshake, and then you can send one message that could have been one single UDP packet. This is why a lot of this is not originally done. Also note that the original security extensions here were almost entirely focused on signatures, and they were not focused on encryption. So integrity, not available, not confidentiality. The support here is also just generally bad. So we're going to pause here for a moment and do a think, pair, share. So how could unencrypted DNS be basically misused? What would it take to do this? Like, what would you need to be as an attacker? What kind of access would you need? And what could you happen to do this? And then, okay, the middle one's kind of just referencing some old slides, and the last one is what attack on privacy becomes possible if there's unencrypted DLS. So the first one is about redirecting the person. It's basically an attack on security. The last one's an attack on privacy. So think about how this can be used. 1 minute. Recording. So I'm just going to quickly repeat the answer because I've turned recording back on. So the top one, you can just swap out the IP address. The next one down, you need to be on the network app. Third one, what technology have we already learned about? The answer is certificate authorities. And the last one, the attack on privacy here is an attack on confidentiality. So the ability to tell where someone is going, and that is not protected by the certificate authorities. So even though I may get a DNS message back, I can detect if it's wrong, I'm still leaking privacy even if I have integrity. And this is why encrypted DNS was a major move by the industry, but we didn't gather get around to that till 2020. DNS is often considered a soft target because most people don't know the IP addresses of the places they're trying to go. You can easily take a website offline without ever attacking the website itself once. What do? You hit the DNS mapping because now it becomes impossible for the average citizen to find the website. In this case, I think this is so I think in this case, yeah, it's denial of service attack. So DYN is a DNS provider. A lot of cases, somebody might have a server, but they don't want to run their own name server. Large companies run name servers. Other people, it's just a waste of their time. So often things like GoDaddy, Namecheap, all this stuff run their own DNS servers on behalf of other groups. In this case, they just DDoSed that name server. So they just slammed the name server with so much packet traffic that it couldn't do anything, and all the websites went offline because no one could look up the mappings. Simple solution. This one, someone just logged into the name provider for New York Times and just changed the end destination. If I remember correctly. Yeah. This caused New York Times to go to an anti-war message page. So again, this is a simple attack. You just go and change it. Yeah, they just send a phishing email, change the DNS records for multiple names, including New York Times. Suddenly, New York Times went offline. You knew the IP address, no problem. it would load. But the name system is now routing to the wrong location, and effectively the page has gone offline. DNS is on soft top. This is also what Facebook seriously mocked up. They took their own DNS name servers off of BGP. So they basically took their name servers and disconnected them from the internet, so they were no longer possible to route to via the BGP network. Now their name servers are destroyed, and no one can resolve any of the names. Okay, any questions on this? Because we're about to move to the fast section.
This is the same for that happened with, you probably studied about this book.
Yeah, you've seen this one before in this class, actually, when we were talking about BGP.
Yeah.
Yeah, this was really bad. It was, whenever you have to take a hatchet to your own server door, you're not doing well. Okay, how web pages are built. Again, this is something I hope everyone in the room knows, but if not, you're about to get a crash course in it. Once you click a link, your web browser will attempt to load a page. Pages are not flat. This is a visualization of a deceased plugin for Firefox. But you can rotate it sideways. The layers you're seeing are divs. Web pages are dynamic. They're constructed dynamically. They're built dynamically. A newspaper and a web page are on different planets because a web page has a whole lot of code behind it. It is also not consistent. If I upload a web page and you load a web page at the exact same time, there's zero guarantee you get the same page. In fact, there's high guarantee you're probably not going to get the same page. So let's imagine this overly simple web page sitting here. This is quite simple. I've even put in fake code in some places, but the point is it loads several images, and it loads some trackers. Let's just go through this. So we have here on the left cutedogs.com. That initial HTML file that you load, index.html, is usually just kind of like a recipe sheet. It's a template, and it contains a mess of instructions in it. Again, if you've ever done web coding, this is old news. But those mess of instructions, your browser is now going to very fast go through and try to follow all those instructions to construct the page. Because it is doing page construction. It didn't load the whole page in one go. It only loaded the instruction sheet. And it's now going to build it. So in this case, the red shaded boxes here are all things that are about to get loaded in. So we start at the top, we load this dog, we load the other dog, we load the style sheet. Oh wow, look, a whole bunch of things just jumped. There's some color now, we got a cute dog picture at the top. But style sheet itself never directly loads in a visible way. It's loading code, which is then impacting the visualization of the page. We load tracker. Oh, did anyone even see anything change? I mean, my little visualization down there, the missing piece went away, but that was about it. It's kind of invisible. It just loaded some JavaScript and tried to run some of that. It loaded an invisible image. What do invisible images look like? They're invisible. You can't see them. You can totally create an image that has hidden in it, is 1 pixel by 1 pixel, and is clear. Totally possible to do. Then we load this thing called connect.js from connect.facebook.net, which helpfully modifies the page to add another thing to our instruction sheet, which now asks us to load the Facebook logo. The main point of this, your browser is doing a whole bunch when it loads a page, and it is making a lot of connections across everywhere. What on earth is a third party anyway? So we talk a lot about first party, third party. First party is that website, that initial thing you get in. Maybe some of the icons you're getting are from that domain, maybe they're not. You actually have huge dynamically created supply chains off of your web pages. Easy, isn't it? So this is Sears.com. This is the full supply chain for Sears.com, probably circa 2012. I have never been able to find this graphic again because companies don't like to give these out. I think they really messed up when they gave this one out. The size of the dots are load time. So this is a company basically trying to sell this product that I'll tell you why your web page loads slow. And it does this by looking, it's a Cloud's plugin, and it's just measuring this from many points on the internet. But this is what the full supply chain is for Sears.com. This is big. Think about some of the things I've talked to you about already. Man-in-the-middle attacks, attack surface. Does anyone like the attack surface here? I mean, do you really want to manage this if you were Sears.com? Yeah, think about some of the other web pages you work with regularly. what their attack surface actually functionally looks like. When we look at a page, loading a page, loading a page, because each of those loads I just showed you, that's the last load. It's quite possible those servers also did callouts on their own. So you end up with this huge graph, and this is a large threat surface. All right, I'm going to do cute dogs loading strategy again, but this time I'm going to use the Guardian. Why? Because I created this slide deck when I was in the UK. For the case of the Guardian, these are all the content sources on the day I decided to do this. I have subdivided them into ones that are owned by the Guardian, broadly speaking. Notice, though, that these are a range of domains. They are not all guardian.co.uk. They are like GUIM, some of them, Guardian Apps, the Guardian. A company can own a lot of domains that are not all the same host. These are the ones that are actually owned by them. Everything else is not owned by them. I'm picking on the Guardian because I did not want to go to the Telegraph. Goodness. And the BBC was too boring. So we're playing with the Guardian. This is the Guardian as you normally see it. This is the Guardian when I cut out everything that's not the Guardian.co.uk. Wow, that got really boring, didn't it? This is what happens when I added things that are owned by the Guardian, so just those green sections. And this is what happens when I add the trackers. What's the difference here? Most of the visualization is actually coming from this ad at the top. Most trackers pretty useful. I don't even know if this app still exists, but this is a plugin on Firefox called Lightbeam. It's changed name several times. I think it's gone out of fad. What it does is it tracks all the trackers. So the idea here is the circles are the web pages I went to on purpose. So we have the Guardian, I think the Register, the Telegraph. That's the Telegraph, there's the Register, there's Guardian, and over here is the BBC. The triangles are all the connections out to different groups. You'll notice that it's formed a natural Venn diagram, hasn't it? In the middle here, these are the companies that know you visited all three, but not the BBC because they're kind of boring in terms of tracking. And then these are the other ones that kind of know you visited one or two. Yes, companies are tracking you. How are they tracking you? Well, your browser helpfully contacted them for you, and that makes it quite easy. So what's one of the big things a lot of people did to deal with this? They installed AdBlock Plus. I have literally been told by Facebook employees that this is actually an extortion scam. That's their view. I will admit it caused a seismic change in the way advertising works across the internet. I don't even know if how many people here have an ad blocker installed? Okay, most of the room. Yeah. You created what we call leverage by installing these things, which caused a massive change in advertising because consumers got so angry with blinking pop-ups scrolling across their screen that they installed this, and then we caused a lot of change.
They're funny too, is a lot of the like age verification laws and ID verifications being pushed by Meta and other social media companies big time because a lot of phone providers have gotten more serious about security than they were in the past, and major revenue drop-offs have happened. So they're legislating people, politicians who are also linked to Epstein anyways, you pay to push these like laws.
As we'll see as we kind of progress, a lot of things have happened to the internet across time. Ad blockers are something I broadly recommend because it just plummets your attack surface. This is what that diagram looked like with just three things. Normally, this is what they look like with AdBlock Plus. Also, before anyone thinks that this is static in any way, this is what happened when I got distracted, wandered off the computer for a couple hours to go do something, came back, and realized that I left this thing running. The AdBlock Plus one barely shifts. One on the left just keeps getting bigger. Each of those websites is a unique website, not a unique load. So if the same website gets loaded 12 times, it still shows up only one triangle and only one line. So it's actually contacting more sites as time progresses. Installing an ad blocker just takes your threat surface and just makes it so much smaller. Okay. All right, we're going to do another thing, fair share. What are those advertising blockers doing? Like, how are they actually doing that? because we learned a lot about networking, we learned a lot about like operating systems, we learned a lot about CAs, we learned about all this stuff. How are they blocking stuff? Yeah, I don't know if we need to think about this. Let's actually just jump to a pair because I have a short amount of time today. So go ahead and talk to your neighbor. How are they blocking this? What does an ad block do? Go. Yeah. On this. There's a lot of different types of ad blockers. Actually, I'm on the wrong screen. There's a lot of different types of ad blockers. The ones that are in browser, like AdBlock Plus, usually operate using a range of things. So one, they usually have a long block list of just things they don't want to load ever. But how do you generate that across the entire internet? Because the number of trackers is insanely large, and honestly, those trackers are doing randomization. So they are making it very hard to identify them automatically, which means the second round of what they do is crowdsourcing. So a lot of the ad blockers have modules or something you really haven't noticed where you can right-click on any ads you see and report them. AdBlock Plus is a very special case. Remember, I called them an extortion. This is because they actually don't block all ads. They block annoying ads. And if you're a large company of, say, Facebook or Google that have a lot of ads, you can pay them a good bit of money to assess your ads. And if your ads are deemed to be not annoying, they will allow them through. So AdBlock Plus's financial model is to go and make sure that you don't get annoying ads, which is different from not getting ads, and why Facebook considers them to be extortion racket, because Facebook pays them money to let the ads through. It's kind of interesting. But if we come down this a little bit further, what about DNS? How could I use DNS this way? How many people are doing this already? I was expecting the front row to raise their hands, and this did not occur. Okay. I prepped this. Drag.
Are we talking about like DNS holes and stuff like that?
Now I'm talking about this. Oh my, I have a lot of these things up. I take notes after all the different lectures, which is what you're looking at up here. But this is the host file from my Windows machine. Can anyone tell me what this file is doing? So, I started this lecture by making a point that the internet is just sitting on top of an entire network stack. Things like AdBlock Plus are living all the way up at the top of this application layer, the very teetery top of that network stack. They are doing things like blocking the connection before it ever leaves Firefox. But after it leaves Firefox, it has to travel through that whole OSI network model, doesn't it? It gets things added, it gets things put aside, and as a component of that, Firefox is usually not handling the DNS. It's allowing something lower level to do that. So when Firefox puts out a request, can you please load this tracker? That's not the end of the story, right? It has to go down again through the entire OSI network stack. I talked about caching, and I talked about caching with DNS. Your browser, so if it has a cache for DNS and someone's attacked the DNS server, you can still access the website, because you still know what the IP address should be. One of the things your operating system maintains for you is a set of hard-coded DNS mappings. What you're looking at this screen is me hard-coding adframes.source.com to 0.0.0.0. Look back. I'm basically saying that if any program on this entire computer attempts to access this site, make an error. So now it does not matter if it is an app, it does not matter if it is Spotify, it does not matter if it is Facebook, it does not matter if it's Firefox, it does not matter whatever it is, if it's going down through my operating system's DNS resolver will resolve adhall.com to 0.0.0.0. Man, this is so nice for Spotify. Like, the number of ads I've had since doing this has like plummeted to like half to a quarter because it can't get off the computer. You can do ad blocking at so many levels. this is an attack on the advertising network via the host file on my local machine, in which I am simply mapping all known advertisers to nothing. This is hard to maintain them because it blocks a lot of them, but they pop up all over the place. So yes, I also have an atlas. But this is an example of how you can use DNS to do this. Oh, how do companies like Facebook and Google verify that their ads on their platforms are safe? So one of the things that I showed you a bit earlier here, just going back, is this diagram. Software supply chains are a total nightmare. And advertising is also a total nightmare because advertising is usually done via live bidding. So if you load a page, a live bid occurs amongst a bunch of computers over who's going to go and get to show you an ad. And where does that ad load from? Does it load from Facebook? No, it usually loads from one of those things I just showed you, an advertising network that manages these things. It's actually very hard for groups like Google and Facebook, and etc., to go and figure out which ads are or are not safe because they are being loaded directly by your browser and not through Facebook or Google. That means the code for that ad starts at the location and then loads straight to your computer. It does not go through Google's scanning or anything of that nature. Google does use things like Chrome to help it figure out what the end source looks like for some of these things, but there's not a lot of stuff that can actually help you with this. And weirdly, the slide I normally show here is, okay, I'm going to jump to a different slide because it's making more sense at the moment. This is a famous attack that happened on yahoo.com. They were hit with a malware attack. Malicious payloads were being delivered to around 300,000 people per hour. So they were pushing malware to 300,000 people per hour. The company guesses that around 9% of those, so only 27,000 people per hour, so only a small town per hour, were being impacted. The difference? Oh, sorry. The difference between those two is that the people being impacted hadn't pushed updates, which is why I normally use these slides. But what's going on here is that clients visiting yahoo.com received an advertisement by ads.yahoo.com. How are they delivering 300,000 an hour payloads attack to people? They just paid for it. They just said, Yahoo, will you please send these ads to people? And Yahoo was like, sure, give us some money. We'll totally send it. And it turned out to be malware. They're not necessarily great at this.
What year is this?
Oh, this is a while ago.
The Yahoo was still.
No, Yahoo wasn't even that much of a thing. I want to say this was closer to like 2014. Yahoo's more of a thing than you realize, actually. I know a security researcher working at Yahoo's. Yahoo Mail is still huge. I had a nice chat with one of their security researchers, and they're like, scale. You cannot go and figure out whether or not something is phishing at scale, such that 2,000 people do not all email or help desk at the same time when their email goes busy. Yeah. All right. That was this point. We're now back over to web page building. I'm just definitely checking that I am actually recording again. So we're back to this concept. Third parties. Yes, we are recording. Every content request is sending a connection. Every content request is perhaps sending up a TLS connection. There is not one TLS connection for your website. There's like 20. And every single one of these sends information. It's not here, I'm only IP address 192.97.124.26, right? That's not the only fact that's sent, actually. A lot of information is sent. This is a line from a standard Apache log. More information than this is sent, but this is a good example of the information readily available to almost every web page out there running Apache, which is a large number. So includes things that take note. The response code set to 200 means that this web page is successfully sent correctly and not a problem. The response size, and the user age is straight. For historical reasons, it always says Mozilla. So you pretty much ignore the Mozilla component. This is because it broke something a long time ago, and now everybody just does this. So this particular web request is being sent from Windows NT. It's got the exact version number, and this was Firefox version 128.0, I guess. So you get a lot of information. And you can pretty easily tell apart who's visiting you. So this is like Firefox and Android web. You can see how they're all starting with Mozilla 5, but you can pull apart each one. This is an attack attempt against my website. I can tell you it's an attack attempt because the web page they're trying to get is login.php, and I don't run any PHP. There's no reason to ever try to access a non-existent PHP, so this is totally an attack. And right below it is a spider. Now, if you look at my page, like half of it's bots. They're just trying to access the page. If they're nice, they self-identify. If they're not, you can tell that they're bots because they're accessing things that no one will bother with. That stuff I showed you, you're probably thinking, Cammy, this is unexciting, but it is sent with every single piece of content. And that means that every web connection is sending this information. This is how tracking is done functionally. Because if I load an invisible image from my web server, now for that cost of that invisible image, 1 pixel by 1 pixel, I get to discover what web browser you're using, what your IP address is, a lot of information. And this is how web tracking functionally works, is that main website lists you as a tracker. That tracker loads an image, and then all that information is sent. What's also sent is cookies. All right, here's a crash course on cookies. Why do we have cookies? What do they actually do? And why is it hard to get rid of them? I'm a bit odd. I actually really like cookies. Cookies are actually a beautiful example of an engineering decision that's intended to both cause the functionality we want, while also protecting consumer privacy. You may think I'm insane because the cookies are readily used to destroy consumer privacy. But actually, if you look at their design, they could have been designed a lot of other ways. And this route was selected explicitly to try to help protect consumer privacy. So back in 1994, when we were trying to invent this thing, the internet was kind of old, and we had this problem. It has no memory. It's a lot closer to picking up a newspaper. You go and you visit a web page, it has no idea who you are. And keep in mind, at that point in time, it's quite likely that 6 people are using the same computer. So the IP addresses are also kind of useless for identifying who someone is. It has no memory. So you end up with this sort of situation. Hello, web server. Hi, new person. What's your name? My name's Bob. Hi, Bob. And it's capable of doing this because it does have things like get and post strings. So it is possible in the URL or in the connection to maintain some information back and forth. And so you can do this through a singular connection. But all it takes is one page reload or turning off the browser and starting it up again, and we get this again. Hello, web server. Hi, new person. What's your name? My name's Bob. Hi, Bob. No memory. And this is problematic. It's problematic because we want to sell stuff to people on the internet. So we really need shopping carts. We need the case where you can kind of load up some items and then maybe pay for them tomorrow. And this is perhaps the biggest marketing push behind doing this. Now there's an obvious solution. By the way, this is the solution chosen by Android. We could just get every browser unique identifier. There is one on your phone. There's one on your Apple device. Keep this in mind. Hello, web server, ID 1234. Hi, new person, what's your name? My name is Bob. Hi, Bob. Tomorrow. Hello, web server, ID 1234. Hi, Bob. Would you like to buy the shoes you look at? Right. We can totally sell things to people now. This is great. But we have a small problem with this. Now it becomes a case that hello, web server 2, ID 1234. Hi, Bob. Your ID is known for liking shoes. Because it's now entirely possible to sell your information across the internet because you have unique specific ID. Wow, this sounds a lot like what happened with Android. Anyway, but this was made by Netscape Navigator at the time, and they were not a large company. They really did want to support privacy. So they decided instead to create cookies. So cookies are a small text string that the server can ask the browser to remember and give back later. So this is how it goes. It goes, hello web server, hi new person, what's your name? My name's Bob. Hi Bob, please send a cookie with Bob as the string. 1 day later, hello web server, cookie Bob. Hi Bob, would you like the shoes you looked at yesterday? Now the advantage here is that now this happens. Hello web server 2, hi new user, what's your name? Because that cookie is only given to the domain that originally sent it. Okay, we all got it still here. So now the idea is that I can create a unique ID for any given domain, but it is only for that one domain. It is not persistent across the entire interaction with every single domain. And this is the point of cookies, and this is the design decision that promotes privacy. Cookies have gone through a lot of changes in the last several years. So this is a true statement at the time of what I'm describing, and I will get to that in a moment. So clients, not servers, manage cookies. So tracking is also visible to the client. Why do you get all these notifications about cookies? And how many people have ever notified you about your ID unique identification on Android or iOS? You don't get notified about that because it's not being sent into your space. It's being managed by the operating system on your behalf. One of the nice things about cookies is they are living in user space. You can go look at them. A journalist can go look at them. Lots of people can go look at them. Researchers can go look at them. And we can see the tracking visible. When it's being done through unique identifiers for a browser, we can't see the tracking. It's all living in back-end databases. Also, you can totally just delete a cookie. If you delete a cookie, they just forget who you are. You can just break it at any point and be like, you can reset the unique identifier. Huh? You can reset the unique identifier. An old tactic before security became a thing at all was just go in and modify the prices of items. So some poor designers would think about, I want to create a shopping cart, I'll just post the shopping cart, you can say what item it is in there, and you can say the price. If you just go in and edit the price of the cookie, and the server would believe you. It was awesome. We fixed that a long time ago. One of the key things though in access control is that cookies are access control managed. So they can only be read by the website session. And this is a very important point. You can also look at your own. I have an entire activity on cookies. You can go run it. All right. We're going to go through this. Okay, we're going to try to go through this. So we have this dogs.com. We kind of did it initially. It's a totally fake site. So let's look at this, like what this looks like in terms of connections and in terms of cookies. So initially the browser contacts that website and it has a couple cookies. So it might have a unique identification code at the top. It might have a language. Language is a common thing to put in. Not everything in cookies are identifiers. That comes back with maybe a session cookie. Session cookies are used a lot to identify who something is, or who someone is across reloads, because the server is stateless. It has no clue if you're the same person or not. So we commonly use called session cookies, which is a unique code indicating which one. Then it turns out we want an image, so we go contact the Instagram server. Instagram is a different set of cookies. They can't get the session cookie, they can't get the other stuff because these are access controlled. It also sends back the image. Maybe we contact this tracker, we send a tracking ID, we get that back, along with this little blank image thing. I'm ignoring this thing back here. So cookies are only readable by the site itself. This is very important. Even if I have two different things. So what you're looking at here is two web pages I used to use for teaching. One says hello Cami. You enter your name and then it says your name. So this would say hello Cami. This is on Banyay.com. There's also another one on CamiBanyay.com. Both different identifier. Two different websites. And the picture I thought I was about to see is actually with an iframe. So if I go and I put an iframe in the middle of one of these, so basically I carve out and put a website inside of a website, it will show two different cookies, even if it's running identical code, because it is still getting cookies from two different places. So one tricks though is, okay, I keep telling you on this, these are access controlled, but you better bet that companies are finding a way around that. So how are you finding a way around that? How are you able to go and take this type of code I have, say send to only one page, and send it to another? And the key point is that it's a dynamic web page, right? It's running code. It's not being sent to something that's being run by the browser itself. It's being sent to something that's running happily JavaScript. So site A is being loaded by the browser. Site B may be contacted to retrieve content. And when site B is contacted, all of site B's cookies are sent to just B. Sorry, that was the web page I was looking for. This is me just demonstrating what a session cookie looks like. The short answer is I've done research with session cookies, and they're a nightmare to define properly. They're mostly just short-lived. They either don't have a length or they have a very short length of time to live. They're hard to define, but there's a couple other interesting things on here. So, sorry, I was prepping the beginning of this. I didn't think I'd actually get this one. So that's good. Sheet, look ahead. Okay, this is the boring stuff. We'll go through this briefly and then move forward. So session cookies. So here are two of their used by UW Learn. There's a couple interesting things here. So HTTPS only is set to false, and over here it's set to true. It is the case actually, and similarly with the secure state. I forget which of these it is, but it's possible to actually load a page where the page is over HTTPS, but the cookies are set in the clear. This was a common problem for a while. There's this program called Firesheep. Firesheep was something you could run if you were sitting in a coffee shop, and it would let you collect all the session cookies from Facebook of everybody else in the coffee shop, and then just log in as them. Because you're from the same IP address and you have the right session cookie. So it would just let you log in and you can start logging in as everybody around you. Why? Because cookies are another example of something we encrypted the main thing and we forgot to encrypt the cookies. So there's actually ticks in here about whether or not you want your cookies encrypted. Because why would you not? All right. So we can do basic attacks against privacy. So here, this is the diagram I dynamically built half a moment ago. You notice that everything is getting its own ID. But everything is getting its own ID, everything's setting its own ID. Okay. So here we're using the QDog server over here. Let's say I go to a different web page. So now I'm on a completely different page. I was on QDogs before, I'm now on my page. This tracking ID being sent to DoubleClick is 758. Here it's 758. Oh my goodness, it's the same. And no, this was not a mistake by Cami. The same cookie is sent to the same site, irregardless of what the main site is. And this is the thing that's changed in modern times. So for a very long time, if I'm on my bank and they're using a tracker, and then I go over to QDogs and they're using the same tracker, that same tracker is sent the same ID from both points. This makes it possible to track people across the internet, and this is the problem. Blocking this is incredibly technically hard. So it's trivial to just block it. That's easy. We can just cut connections. We're good at that. Blocking it without destroying user experience is really hard. Let me give you a very basic example. Let's say I want to log in with Facebook. What am I going to do? I'm going to log into Facebook's website, and then I'm going to need to be able to send messages to Facebook periodically to check that I'm logged in. And I'm going to be doing that from a network host site. If I cut off all Facebook connections for privacy reasons, I also cut off the ability to log in with Facebook and maintain persistent login. That breaks the internet. I have not had the time to really dig into how Firefox is doing isolation right now, but the last year or two, several web browsers have started doing more advanced isolation of cookies. So it is now the case when you go and load a web page, it sends an ID to DoubleClick, and you go to a completely different page on a different tab, and it will send a different ID to face. It will basically treat it as if it's new. I haven't done a research project in the space that time frame, so I'm not actually tracking it. But this is how tracking is done across web pages. That's just an example. That's double click sitting there. It knows from every single one it's being sent the same IP address from your browser. All right, we are rapidly running out of time, so I'm going fast. There's also nothing stopping your web page from copying stuff in circles. So let's say that I go and I contact my bank here. I give it some ID numbers. It goes and sets a session cookie. Now, when it sends a message back, it's not just sending this session, it's generating the HTML. Now, that index, again, if you're in web design, you're quite aware that that's not a fixed page that's being sent. It's actually dynamically generated by the server. So the server takes in this information, like your ID number and stuff like that. It creates that web page. There's nothing stopping it from modifying the get strings on components of that page. So now this component that is random number here is actually this is a customer of my bank. Given this content. So what's happening now is that bank server is coming back and saying, okay, here's the thing you need to fill in, here's the unique code. Your message then goes out to a content network, for example. It could be any third-party server, but it's a content network, and it says, okay, these images need to be served to this type. And that is a way in which that bank is actually directing another page via your browser. A different customer might be given a different code, and different content will be loaded from this. This is totally benign. What gets interesting is when we bring double-click into it. Because it is entirely possible for that my bank server to also drop in information like this is customer ID 2796 and put that in the link to the double-click server. This allows them to basically say, okay, this consumer of my bank is actually linked to this particular browser instance. Let's see. Oh yeah, no, this is a famous case. This is a famous case of this. So healthcare.gov, which is the healthcare website for the US, right after it launched, people were kind of digging around in this, and they found this fascinating bit down here of the get string. In which it's sending a message. So DoubleClick, I keep picking on DoubleClick. DoubleClick is a very famous tracker. It is owned by Google, by the way. There's a lot of litigation on DoubleClick, so it's a bit more complicated than the normal one. It's sending a lot of information, right? It's sending what website the person's on, what state they are, the results, the country, their age, whether they're a smoker, whether they're a parent, whether they're pregnant, their zip code, their state, their income, and what step they are in the application process. And all of this is being sent to a tracker by a US government page. You are all staring at me in horror. I am in the middle of going and running studies on Canadian government sites, and an embarrassing number of them are using Google tracking. This is a common thing, but this is one way information that's originally stored on one page might be sent to a tracker. And it's, yeah, this is a very famous case. You can also do cookie syncing. Got an example of cookie syncing here? Yeah, okay. So the browser sends user ID 47854 to my bank. My bank then again generates that index file. As part of that index file, it creates a get string that says UID 47854. Oh wow, it's the same ID number. And sends it to DoubleClick. So in this way, and this is actually done actively by a lot of trackers right now, is that you insert some amount of tracker code into your web page. One thing that code does is it requests that a cookie be set, which it can do because it's a first party, because it's in the first party page. It sets that cookie. On next page load, that JavaScript reads the cookie, because again, it can, it's the first party page, and then it dynamically creates another web request added to DoubleClick, which contains that cookie. And this is one of the other ways it's getting around both the prior protections of page lockout and the modern protections we are seeing from groups like Facebook. It's now a first party request. All right, we are short enough on time. I'm going to just glance at what the rest of this has to say. Oh. All right. I cannot do the Verizon super cookie in this short time, but I will do a quick look ahead of it. So if you've looked at the final exam from last year, you'll notice the Verizon super cookie is an entire massive question. How this thing actually ran was something I was talking about a lot. I'll probably talk about it again later. The idea here is that if Verizon used a man-in-the-middle attack to inject a cookie into web requests. So the idea here is we've been assuming the cookies originate from your browser. What would happen if a cookie didn't originate from your browser? And I talked a moment ago about how you can send cookies without being HTTPS, even though the whole rest of the page is HTTPS. So what's stopping Verizon from dropping an unencrypted cookie into a connection alongside your encrypted stuff? And so they were caught actually going to basically selling their customer data linked to these web requests. And that's a really fascinating case that I'll get further into later. And that is the end. Barely just in time. All right, thank you so much. I deeply hope that come Monday we do not have this amount of smoke. I will be paying attention to any announcements by the university, but the university seems to think its air filters work. If I think that it's really terrible air quality, I'll do what I did again today, where I just promised to do more recording. All right, I'll see you on Monday.
Probably gonna rain tomorrow, so probably.